weird. And I had to ask him what it is and how to actually look at it. But basically, I had to add.
Well, thanks again for finding an opportunity to invest your time in visiting this meetings.
Yeah. So the combination of 8. Oh, 3.
So, who we are and what are we doing? We are doing the same thing as we did in the lab, but with more boring for everyone except professional mathematician way. So, we want to be masters of space and time and predict the future, at least in some limited cases, for molecules, nanostructures, and maybe some simple models that describe them. And right now, our guinea pig is a claustrophobic electron confined to the walls. So we are going to predict how it will evolve in time. And if you have attended the night session, evening session on Wednesday web, then you kind of expect what we will get on the screen. The only difference is that in the lab, it was super easy and quick, just hit the button and watch the movie. Now we will suffer mathematical derivations, but the answer will be the same. So you recognize your plan of putting everything you did in the lab into Word or PowerPoint thing, print and bring it on Wednesday. So just a little navigation about our place in this world. So we can set up an axis of methods, axis of molecules or real systems, and then there will be a third axis that we do not care right now. And if we look through the methods that we have learned, like evolution operator, time-independent Schrödinger equation, time-dependent Schrödinger equation, Heisenberg equation of motion, and then we look on different models, we see that, okay, we take one of the methods from our toolbox and apply to one of the systems. And basically, through the rest of the course, we are going to expand the space on this image. So, same methods for more and more systems, or alternatively, if you would not care about real world, we would take one system and apply new and new methods. And then when we expand far enough, we may realize that systems are not isolated. So we did eigenstates analysis for free electron. Then we did time-dependent Schrödinger equation to see how it expands, right? Free electron. And then we did very short overview of Heisenberg equation of motion to see how the center of the wave packet of this electron in free space moves, right? So it is what we have. Now we started confined claustrophobic electron in a box, and we looked for eigenstates, and now it is time to look onto the time evolution. This image blocks, but there is one more circle in here. You see there, we will not specifically invest time and slow down our progression, but as we go, we will get acquainted with one more method that is helpful too for time dependence. So those are two equations that we all kind of remember from last meeting, right? So probably you can memorize or you can find it. We are not going to make a quiz and check how our memories are. And in case some of you are looking into teaching career, then you may plan on how present this information in a condensed way, in more condensed way. Like right now, we have a luxury to spend hours, and sometimes one needs to squeeze quantum theory in maybe 2 hours. Everything. So then, instead of appealing to analytical part of the hemisphere of the brain, you just try to connect to immediate associations and some visual progression that a person will memorize without thinking deeper. So let's quick look on particle in the box from this visual progression. So we do have this sign functions, and we do have energies. Two things that are too much, two figures to represent them, but too much. Can we merge them? And you may have seen it. Every textbook does it. So we can set up x-axis as position and y-axis as ambiguous axis. On one hand, it will be energy. On another hand, it will be either wave function or probability density. So you kind of add together energy and probability. Do not say it in public. I will remove it from recording, but it is what most of images in textbooks do. You will see those images, where energy is added together with probability. It's not good for verbalizing, but good just for quick going over. So those are functions without offset, right? So sine function for the half of period, and it is 0 at the edges of the box. And we do have the n square, and the rest are constants, like size of the box, Planck constant, what else? Mass, 2n each per square, but it is important that it is n square. So if you set up the energy for different n number of eigenstate, it will be proportional to 1 square, 1, another 2 square will be 4, 3 square will be 9, so you'll see that offset increases. Right? And to communicate this idea at once, typically one makes these offsets, which become bigger and bigger, and on these lines one starts to draw functions. You have seen it, right? And then you can either plot functions or probability squared. And this philosophically wrong approach is so loved by all textbook authors that you will see it again and again for different systems. If you look for more complicated systems, you still will see these figures. Any objections or questions about this silly stuff? I will not ask you to draw it this way in the future, but you may just feel comfortable if you see what textbooks are showing. So basically, they are wrong. They show x-axis as energy plus probability. I don't know how successful I will be in keeping being organized, but an attempt is to have a running panel that shows how far we are progressing. And right now we are trying to go into the time evolution. So we select some non-initial state, which is not an eigenstate, because if a system is in the eigenstate, then it is boring. You do not need to do anything. It stays there. But if it is a superposition, if the system is in the state which is not an eigenstate, then something will happen with time. Make sense? We cannot be too, well, we can, but it's too hard to be too general. Let's make a case study. So which initial condition we can set up, identify. So if you look on our wrong diagram with energies and probabilities at the same time, and then we can bring in an external problem maker, like laser. So we point laser on the state, on the system, and typically light does what? Huh?
Excites.
Yes. So if we shine long enough, we may convert some portion of electron with some probability to the excited state. But if the light is weak, or we apply it for not long enough, then it will be a smaller portion of probability, right? Or like. So why don't we take it as our initial condition? So we have 50% ground, 50% excited, and see what happens. Does it appeal to your common sense that it is more or less a reasonable problem? So you cannot expect that if you do arbitrary experiment, you have always 100% there or 100% here. Even if you try to excite it there, you may have unclean experiment, optical. It will be not 100% there. So there will be a superposition. So why do we have square root of 2 here?
Normalization.
Yes. So how to prove that square root of 2, 1 over square root of 2 is correct?
Square your wave equations and
Huh?
integrate. Square your wave equations and integrate. I mean,
Yes, but we can set up much easier way to check that expansion coefficients are correct. So instead of integrating over space, we can just add together square and make sure that it is 1. So we can perform normalization in space of expansion coefficients. So C1 square plus C2 square should be what?
1.
1, yes. So 1 over square root of 2 plus 1 square root of 2 will be half plus half, 50% plus 50% will be 1. So totally electron is either in ground or excited. Are you scared by this angular brackets? No, you're not scared because you're brave. And because Andrew?
Yeah.
Okay. He has introduced to all of us the Dirac notation, right? It's for Brian cat. So if you see the right side vector, it means column or function itself. If you have left side, it will be it will be row vector and conjugated function. So this is our initial state. And under this ket vectors, we understand our eigenstates. So expansion coefficients, time functions. So what is our goal? To push the button like let it go. Let the time progress forward and see what will happen. Do we expect to change the ratio, the 50 to 50% ratio between probability of ground and excited states probabilities? Let's practice democracy. Who will vote for probability of electron residing in either ground or excited will change with time? Okay, one. Who will vote that probability of electron residing in ground or excited will stay unchanged?
Assuming no perturbations or anything.
1, 2, 3, 4.5. Okay, by majority we decide that it will not change. So whoever is in minority should accept the opinion of majority and believe that it is truth. Right? But something will change, right? So these coefficients will not change their absolute value, but they will accumulate phase. And then we will see that wave function with this its conjugated complex part and probability distribution will change with time, as well as some observables. So what we do, we are practicing our third way to predict future, right? So in the definition, we add time-dependent factors. So the time-dependent factors do what?
Just hinge in time?
Yes, yes, thank you. Change in time. How do they change in time?
They oscillate.
Oscillate is the, maybe, but if the word oscillation is applicable to complex exponential. Okay, they perform some harmonic change in time, but oscillate is kind of, I agree mathematically, but I feel protest feeling from common sense. So they
Step.
Yeah, I wouldn't feel any protest inside myself if I tell that they accumulate phase, or like this complex factor comes up with different complex phase, something like this. But see, the rate how they accumulate phase is different, right? So what does determine the rate of accumulating phase?
Energy.
Yes, eigenenergies. So each state accumulates phase with different pace. And the space does depend on the eigenenergy. So we can get an answer if we formulate it as a, let's say, homework or whatever exam, and just use our knowledge that we got by now and get the answer same as in the lab. But I'm trying to find if you have any shortcuts, if you can maybe play with notations and make our path shorter and make less mathematical operations. Of course, renaming factors and terms is also some intellectual effort, but I'm trying to minimize like integration, differentiation, so that, and looking forward to apply the same path protocol to more complicated systems. So if we look on this accumulation of phase, we can tell that, it's same shape as before, eigenstates and expansion coefficients. But from now on, the expansion coefficients are time dependent. And so we put it time dependent, and under this C1, we will understand the whole thing that changes in complex plane. And then this will be our future, which is correct but boring. We do not learn anything new. It's not visual, and we cannot draw conclusions. So you may want to see how the probability to find an electron in the left, right, or center of the box changes with time. Will it be static or dynamic? Well, you already know from the lab it will perform some dynamical things. But how do we get it? Probably we need to take wave functions absolute value squared, right? And in addition, we may want to practice our rule of our bridge that connects these mathematical exercises to real life, to observables. So we may want to use this wave function for two purposes. First, find probability distribution as function of position and time. And second, we may find some observable. We select the simplest one, but it could be different thing. So what I'm offering to follow would not look as quickest and most intuitive thing, but later you see benefit. So instead of going directly to this probability distribution observable, let's do an experiment and find the dyadic product. So from your MATLAB session, you remember if you do Bryant cat, if you do row by column, you get a number from vectors, from wave functions. If you do cat by bra, you are getting a matrix or an operator. Okay? So it is a little experiment. So here is our normal wave function, and here is our cat times bra. And here is our conjugated wave function. So for eigenstates, we just flip the direction, and for expansion coefficients, I thought someone would decide to choose the course in the middle of the semester. Then you would stop learning and celebrate, and you come. What does star mean?
Complex conjugate.
Yes. Thank you for helping. So what do we observe if we apply this complex conjugate to oscillating exponential? If you have E minus I energy number 1 h power t. If you do complex conjugation, what do we get? Complex conjugation of evolution, of propagation forward in time. So conjugation means flip the sign in front of which thing?
I.
Yes. I. Flip the sign in front of I. But we can treat it as we still have the evolution of minus I E1 over h bar, and then our time goes in opposite direction. So complex conjugation, in some sense, it means flipping direction of time evolution, going backwards in time. Or just accept the star notation and tell that we do have this conjugation of the wave function. So I think I have to open the brackets, but they are already here. And you probably believe that they are opened correctly. Right? So 2 factors with 2 terms in each gives 4 terms, right? And here we do have cat times bra, little cat and little bra, for all possible combinations. And 1, 1, 2, 2, 1, 2, 2. And here we have combinations of these expansion coefficients. But since they are, even if you set up initial condition that doesn't have this ugly complex things, due to time evolution, it accumulates something complex. And therefore, we need to carefully look for this conjugation sign. No protests? Good. If I will write nothing but show the slide, then we can go really quick and cover a lot of material. So, what can we expect from this products of the expansion coefficients? So you do see, although the 4 terms is not too much, not too many, but you can observe 2 groups. One group, when the coefficient here and coefficient there coincide, and another group when coefficient with conjugated and non-conjugated do not coincide. So this can simplify our life a little bit. So if the index coincide in this product, it means you do have e to the minus I energy number I divided h bar t times e plus I e sub I. I is not a good number. Let's put n. Otherwise, it will be too ambiguous. N divided h bar t, right? And now you have exponentials with opposite signs in the power, which will be equal to what? Like e to the power x times e to the power minus x, which is e x times 1 over e x equals what? Huh? Yes. So if we use the same indices, well, if we happen to see product of the conjugated expansion coefficients for the same orbital, for the same state, they will give no time evolution. And in some sense, it explains us again from different angle of view why eigenstates do not change in time. So if the system resides, if there is no superposition, if it stays only in eigenstate, then time evolution from this C and C star will result in 1. So nothing will change in time. Make sense? But if you do have the non-coinciding coefficients, that's n, k maybe, then you cannot subtract this completely, this powers of exponential. And then the evolution will be minus I h bar t, and then there will be En minus Ek. So the non-coinciding products of this expansion coefficients will evolve in time according to energy difference between the relevant eigenstates. Enough of Dirac. Let's go to regular functions. And we do see that this thing is represented as summation of 4 terms, and each of the terms can be partitioned on the part factorized, the factor that evolves in time and factor that depends only on time, right? So something that depends only on time and something that depends only on space. So why this shortcut is selected? Why we are looking in this direction instead of quickly doing everything at once? For this test problem, it doesn't matter by which method you do it. You'll get the answer anyway. But if you have like 1,000 states, or at least 10, it will be a little boring to open all these brackets, even if you are programming. So everything that is related to space can be processed, and like if you need to integrate, multiply, even find maybe some expectation values, you can do it before you start time evolution. So you can process all operations related to space and all operations related to time separately. And on this approach, you'll save a lot of, not money, but effort. And your whole time, your brain strength will be not spent to silly activity, but more to something strategic or to pleasant relaxation instead of if you do things quicker. Not now. Now we do it a little bit longer than one can do this problem, but for the future, it is expected to be a benefit. So we do need to multiply conjugated function by itself, and here the indices are either coinciding or not coinciding. Since eigenstates are real, at least in this case, trigonometric functions, then this conjugation would not affect anything for these space factors. So it will be either product of like sine squared, or it will be sine pi xl sine 2 pi x, whatever. So only factors in front of pi will change, but nothing conjugated. Right? So I carefully make these products on one hand. And on another hand, we are looking for the time dependence. So this products of the expansion coefficients. Time dependent expansion coefficients. Forwards. A lot of exhaust on the tongue. It's time to design new name for this products. Did I write it there? No? It's here. So one of the there are two interpretations of wave function squared. One is probability density, no, probability distribution. Another is electron density. The word density comes in all the time. So this expansion coefficient squared has some relation to density, and there is a agreement in the community to call this product of expansion coefficients density matrix elements. Density matrix. 3 words, better. Or if you have all of them together, then density matrix. Density. So when you were in the middle school and looking onto buoyance, pronouncing it right? Floating. Pronounce it.
Buoyancy?
Huh?
Buoyancy?
Buoyancy. Anyone else? Please pronounce.
Is that the word over here?
No, I believe you're correct, but I'm kind of making an average to
Buoyancy.
buoyancy. Buoyancy. Okay. So when you do buoyancy in middle school, buoyancy. The word looks French, like voyage, voyance. You were dealing with regular density, nothing with probability, just density of silly stuff. Which letter did you use for density? Huh?
Wow.
Rho, yes, I agree. Let's use rho all the time here. So density matrix elements with letter rho. So if the indices coincided, it will be rho 1, 1, rho 2, 2. If they are not coinciding, it will be rho 1, 2, rho 2, 1. So all information about time evolution can be stored in density matrix element. And then we will have the rest space depending parts. Where do I write it? No space here. Density matrix element stores all about time. And here is, do you see this little ratings? So if we have the indices here coinciding, then the exponentials cancel each other and we get 1. It's here 1 and here 1. And if they are not coinciding, you see they accumulate phase with the phase proportional to difference of energy between relevant states. Just in case you do not see it here, I just write exponential. H bar E2 minus E1 times time. And if we had a specific initial condition, then it is also accumulated here. We should have 1/2, 1/2 to correspond to initial conditions when it was 50-50 distribution. What's next? We already covered it. So for coinciding indices, no evolution. For non-coinciding indices, the difference of energies dictates the progression forward in time. For the space, well, we spent 38 minutes, but when we were in the lab, probably it took 3 minutes to this point. So you just have products of sine function squared, so it will be this bluish line. Then if you have the excited state, you have this thing with one nodal point and 2 humps. And if you have this transition density, it will be negative. So the diagonal elements are always positive, eigenfunction squared, and off-diagonal spatial part that contributes to dynamics can be negative. So we do not have the answer yet, but we can look forward, analyze, and see what can appear in the next slide or two, or maybe next meeting. Whatever we have for time evolution is a summation of terms. Each term has time-dependent part and space-dependent part. So these space-dependent parts are added all together. They're added together, but factor in front of each is time-dependent. And these time-dependent factors do change. So these functions, they are not just smashed together with factor 1 each, but factor in front can vary, and then these functions can add together constructively or destructively. Especially this thing. So at different phases, different level of progression through phase accumulation, it can change its phase, multiplied by a positive or negative factor, and then it is either added or subtracted to the overall distribution of probability. I should have verbalized it here. Yes. So constructive or destructive contribution from all these functions. And then the level of them being constructive or destructive changes in time. This is the reason for time dependence, for the time evolution. So by majority of votes at the beginning of the meeting, we agreed that expansion coefficient, absolute value of expansion coefficients doesn't change. It will be 50-50 for the rest of the life. But the distribution in space will change because of this constructive and destructive summation of space-dependent part. Make sense? Let's see what I have. Okay, those are verbalization of the sentences. I need to circle it here to have the trace. So, if we add together all these terms, we are going to have the probability distribution as function of position and time. And because of this constructive and destructive contributions, we may see that there are non-equal probabilities to see an electron at left or right side of the box. This procedure, this protocol, will describe mechanistically from background point of view how the electron will move probably from one side to another side. Okay? And I have copy-pasted the movie that we did in class here. I will show it and you know how it looked like. But when it's not enough to make a substantially large chapter, so probably we will get the answer in class on Monday. But the plan is to neglect computers and replace CPU by human brains. So we will get the same, hopefully the same type of evolution of probability distribution just by pen and paper, and analytical, which seems possible. It's nothing but adding together these functions with different factors. So we will do it. Just probably too much for remaining couple of minutes. So what have we done? Where we are? We discussed standard type of visualization of eigenstates in textbooks by having an ambiguous axis, which is at the same time energy and probability. And then we decided to move on from time-independent domain to time-dependent domain, which makes sense only if you have system in non-eigenstate, if you have summation, superposition of several of eigenstates. And as a case study, we selected 50-50 distribution between ground and excited and started to following how it may change in time. We didn't got any answers right now, but we made preliminary steps of separating time and space dependencies, and then we just need to flush them back together. We also got namings for new notation for this intermediate components, which hopefully will be useful in our future life. Half-excited state, time-dependent, spatial factors. And it is what we should see if I have enough skills to run the no. So it is what we should get in our analytical efforts. So there will be larger or smaller probability for electron to be near the left or right side of the box. And contrary to the expectations from our everyday life and classical theory, there will be never probability for bumping literally into the side of the box. So because there is an uncertainty, it starts going backwards when it feels some distance from the box. But if you look on the average, it's definitely some oscillatory motions, meaning like running, bumping into one wall, reflecting, bumping into another, and going forwards and backwards. So here is my favorite slide. Thanks so much for staying here and devoting your Friday to quantum theory and physical chemistry. Have a nice weekend, and looking forward to see you on Monday.
What's it?